What if I told you that right now, beneath the peaceful Swiss countryside, scientists have discovered something so fundamentally disturbing that it threatens to unravel the entire fabric of reality as we understand it? I'm not talking about a minor adjustment to our physics textbooks. I'm talking about a crack in the universe itself, a flaw so profound that it suggests everything we think we know about. Existence might be spectacularly, terrifyingly wrong. In March of 2024, researchers at CERN's Large Hadron Collider detected something that shouldn't exist. An anomaly in particle decay rates. A whisper of impossible physics. A shadow of a force that, according to every equation we've trusted for a century, simply cannot be there. And here's what will blow your mind. This isn't just an academic curiosity. This crack they found? It might explain why the universe exists at all, why you're conscious, and why reality behaves more like a glitch in a cosmic computer program than the clockwork mechanism we've been taught to believe in. The numbers don't lie, but they're telling us something we're not ready to hear. Dr. Fabiola Gianotti, the Director General of CERN, stood before the physics community in April 2024 and presented data that made veteran physicists go pale. Particle collisions at energies we've never achieved before are producing results that deviate from the standard model, our best theory of how the universe works, by margins that are statistically impossible to ignore. We're talking about sigma values that scream new physics so loudly that the scientific community can't plug their ears anymore. But here's where it gets truly unsettling. This isn't just about particles behaving strangely. The pattern of anomalies suggests something far more disturbing, that the fundamental constants of nature, the unchanging numbers that govern everything from the speed of light to the strength of gravity, might not be constant at all. They might be cracking, fragmenting, coming undone at the seams. And if that's true, then reality itself is far more fragile than we ever imagined. Before we dive deeper into this rabbit hole, I need you to do something for me. If this video already has your mind spinning, smash that like button and subscribe, because what we're about to explore will fundamentally change how you see everything around you. And I'm curious, drop a comment telling me which country you're watching from and what time it is there. Are you watching this at midnight, unable to sleep because you're fascinated by the mysteries of existence? Are you on your morning commute, about to have your entire day's perspective shifted? Let me know, because we're all in this cosmic mystery together. Now, before we can understand how everything might be unraveling, we need to understand what's supposedly holding it all together in the first place. And trust me, even the foundation is stranger than you think. For over a century, we've believed that the universe operates on a set of unshakable rules. 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These are the invisible hands that shape literally everything from the atoms in your body to the galaxies spinning through space. Physics, we've been told, is about discovering these rules and writing them down in elegant equations. Once we know the rules, we know the game, right? Wrong. Here's the first twist that should make you question everything. These fundamental forces, they're not actually fundamental at all. They're emergent properties of something deeper, something we've been calling quantum fields. Think of it like this. Imagine reality as an infinite ocean, and what we perceive as particles, electrons, quarks, photons, are just ripples on that ocean surface. The ocean itself is the quantum field, and the fundamental forces are just different ways those fields can interact with each other. This isn't science fiction. This is the standard model of particle physics, developed painstakingly over decades by brilliant minds like Murray Gell-Mann, who predicted the existence of quarks in 1964, and Peter Higgs, who theorized the Higgs boson, the particle that gives everything else mass, in the same era. The Higgs boson wasn't confirmed until 2012 at CERN, almost 50 years later, when the Large Hadron Collider finally had enough power to create the conditions necessary to summon it into existence. And here's what's mind-blowing about that discovery. When they found the Higgs boson, it wasn't just a victory lap for physics. It was a warning sign. The Higgs field, the quantum ocean that the Higgs boson ripples upon, is what gives particles their mass. But the calculations showed something deeply unsettling. The Higgs field exists in what physicists call a metastable state. Think of it like a pencil balanced perfectly on its tip. Technically, it's stable, but the tiniest disturbance, and it falls. The Higgs field is that pencil, balanced precariously in a state that's stable enough for now, but could potentially collapse into a lower energy state at any moment. If that happens, if the Higgs field collapses, it wouldn't just be catastrophic, it would be reality-ending. A bubble of true vacuum would expand at the speed of light, rewriting the fundamental constants of nature as it goes, and everything in its path would simply cease to exist as we know it. Atoms would unbind, chemistry would rewrite itself, life would be impossible, and there would be no warning, no escape, because the bubble would move at light speed. The end of everything would arrive without notice. But don't panic yet. The odds of this happening in any time frame relevant to humanity are astronomically small. The universe has existed for 13.8 billion years without collapsing after all. The problem is, what CERN has found might be changing those odds. And that brings us to the crack. Let me paint you of what's actually happening at CERN, because the scale of what they're doing is almost incomprehensible. The Large Hadron Collider is a 27-kilometer ring buried 100 meters underground on the border between France and Switzerland. Inside that ring, protons, the particles at the heart of every atom, are accelerated to 99.9999999% of the speed of light. When they're moving that fast, time dilation kicks in so severely that from the proton's perspective, it circles the entire 27-kilometer ring in about 90 nanoseconds. But from our perspective, it's traveling so close to light speed that it's essentially frozen in time. Then, they smash these protons together. The energy released in those collisions is so immense that it recreates conditions that haven't existed since the first trillionth of a second after the Big Bang. In those brief moments, we're talking about time periods so short that more of them pass in 1 second than there have been seconds since the universe began entirely new particles spring into existence, live their impossibly short lives, and decay back into energy. Dr. Kyle Cranmer, a physicist who worked on the Atlas experiment at CERN, once described it like this: "We're not just studying particles, we're interrogating the vacuum itself." Empty space isn't empty. It's seething with virtual particles, hopping in and out of existence, borrowing energy from the universe and paying it back before anyone notices. What we're doing is catching them in the act. And in 2024, they caught something they weren't supposed to. Something that can't exist according to the standard model. An anomaly in the decay patterns of W. Bosons, the particles that carry the weak nuclear force. Here's where it gets technical, but stay with me because this is crucial. When particles decay, they follow strict mathematical rules. The standard model predicts exactly how often certain decay patterns should occur, down to incredible precision. It's like predicting how many times a coin should land on heads if you flip it 1,000,000 times. You know it should be around 500,000, and if you get significantly more or less, something weird is going on with your coin. In April 2024, the CMS detector at CERN published results showing that W bosons were decaying in ways that deviated from predictions by 7 standard deviations. In statistics, 5 sigma 5 standard deviations is the gold standard for declaring a discovery. 7 sigma? That's not just statistically significant. That's screaming something is fundamentally wrong with our understanding of physics. But here's what truly makes this discovery earth-shattering: a pattern of deviation. It's not random, it's structured. It suggests the presence of something we haven't accounted for. Either there's a new particle we've never detected before, or, and this is where it gets existentially terrifying, one of the fundamental constants that govern particle decay isn't actually constant. It's varying, cracking. Think of it like discovering that the mathematical constant pi, which we use to calculate circles, and which should be the same everywhere in the universe, suddenly starts giving you different answers depending on where you are. That's the level of foundational wrongness we're talking about. If the constants of nature can vary, then everything we've built on top of them, every theory, every prediction, every technology is built on sand. Now, I want you to pause for a moment and consider what this means. You're sitting there, watching this video, made of atoms that are supposedly governed by unchanging laws. But what if those laws are more like suggestions? What if the universe is improvisationally making it up as it goes along? The implications cascade outward like ripples from a stone thrown into still water. If the constants of nature can vary, then the anthropic principle, the idea that the universe seems fine-tuned for life because we're here to observe, it might be backwards. Maybe we're not observing a fine-tuned universe. Maybe we're observing a universe that's actively adapting, changing its rules to accommodate the impossible. Consciousness, observation, existence itself. This is where physics stops being about particles and forces and starts being about the deepest questions humans have ever asked. Why is there something rather than nothing? Why do the rules of reality allow for beings who can contemplate those rules? And what happens when we discover those rules aren't rules at all? Let's talk about what the Standard Model actually is, because once you understand what it claims, you'll understand why these anomalies are so devastating to our worldview. The Standard Model is essentially a catalog of reality's fundamental building blocks, organized into an elegant, symmetrical structure. It's been called the most successful scientific theory ever created, predicting experimental results with accuracy down to 10 decimal places. Here's how it works. Everything in the universe is made of matter particles called fermions, which come in two families, quarks and leptons. Quarks bind together to form protons and neutrons. Leptons include electrons and neutrinos. Then you have force-carrying particles called bosons, photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak force, and the Higgs boson giving everything mass. Gravity is the weird outlier, still not fully integrated into the model. For decades, this model has been tested and retested in particle accelerators around the world. Every prediction has been confirmed with stunning precision. When the Higgs boson was finally discovered in 2012, it seemed like the final piece of the puzzle had clicked into place. Physics wasn't over, but the basic framework seemed solid. Except it wasn't. Even before these new CERN anomalies, there were cracks in the foundation that physicists were deeply uncomfortable with. Let me tell you about some of them, because they set the stage for understanding why what's happening now is so significant. First, there's the hierarchy problem. The Higgs boson has a mass of about 125 GeV electron volts, a unit of energy physicists use. But according to quantum field theory, virtual particles should be constantly interacting with the Higgs field, pumping enormous amounts of energy into it. We're not talking about a little energy. We're talking about energies at the Planck scale 10 to the 19 GeV. That's 1,000 trillion times heavier than what we actually observe. For the Higgs mass to be what it is, there has to be an almost miraculous cancellation of quantum effects, fine-tuned to 1 part in 10 to the 17. That's like balancing a pencil on its point. But the pencil is the size of a galaxy, and the point is the width of an atom. Physicists hate this. It feels contrived, unnatural, like the universe is hiding something. Then there's the strong CP problem. Without getting too deep into the weeds, CP symmetry is a fundamental principle suggesting that the laws of physics should look the same if you swap particles with antiparticles and flip everything in a mirror. The weak force violates this symmetry, which is weird but understood. But the strong force, which is a trillion times stronger than the weak force, should also violate CP symmetry according to the math, yet it doesn't. The parameter that would cause this violation is measured to be 0 or at least smaller than 1 part in a billion. Again, this feels suspiciously fine-tuned. And then there's dark matter and dark energy. The standard model accounts for all the matter and forces we can directly observe. Beautiful. Complete. Except it only describes about 5% of the universe. The other 95%? Complete mystery. Dark matter is some invisible substance that we can only detect through its gravitational effects, making up about 27% of the universe. Dark energy is even weirder, an unknown force causing the expansion of the universe to accelerate, comprising about 68% of everything. The standard model has nothing to say about either of them. Dr. Lisa Randall, a theoretical physicist at Harvard, put it bluntly in a 2023 lecture. The standard model is like a beautiful house with most of the rooms locked. We can describe the rooms we can enter with exquisite detail, but we know there's more to the house than what we've seen. And every time we think we're close to finding the key to those locked doors, we discover there are more rooms than we thought. What CERN has found might be that key. Or, more unsettlingly, it might be evidence that the house is built on a foundation that's crumbling. The W boson anomaly I mentioned earlier? Let me give you the specifics, because the details matter. The W boson is one of the carriers of the weak nuclear force responsible for radioactive decay. When scientists at CERN measured its mass with unprecedented precision, they found it was about 0.1% heavier than the standard model predicts. That sounds tiny, but in particle physics, that's a chasm. That's the equivalent of predicting someone is exactly 6 feet tall and then measuring them at 6 feet 4 inches. Close, but not close enough. But the mass discrepancy is just the beginning. When they looked at how W bosons decay, the particles they turn into when they cease to exist, the patterns were all wrong. Specifically, W bosons were decaying into quarks and leptons at rates that didn't match predictions. Some decay channels were too frequent. Others were too rare. And the pattern of these discrepancies suggested something profound. There's an interaction happening that we haven't accounted for. Something is coupling to these particles that isn't in our equations. Dr. Ashutosh Kogwal from Duke University, who led one of the teams analyzing this data, said something in a press conference that should have made headlines around the world. What we're seeing is either a systematic error we can't identify, or it's the first glimpse of physics beyond the standard model. And given how carefully we've checked our work, I'm increasingly convinced it's the latter. New physics beyond the standard model. What could that mean? The most obvious possibility is a new particle, something we haven't detected yet that interacts with W bosons in ways we haven't predicted. Physicists have proposed candidates: Z prime bosons, leptoquarks, supersymmetric particles. But here's the problem. If any of these existed, we should have seen other effects by now. The data should be littered with their signatures. Instead, we have this one glaring anomaly and nothing else. It's like finding a single footprint of a creature that shouldn't exist and finding no other evidence of it anywhere. The alternative explanation is more disturbing. What if it's not a new particle at all? What if it's a crack in space-time itself? Stay with me, because this is where things get truly mind-bending. Space-time isn't just an empty stage where particles perform their dance. According to Einstein's general relativity, space-time is a dynamic entity that can bend, warp, and ripple. Massive objects curve space-time around them, and that curvature is what we experience as gravity. But Einstein's equations assume that space-time is smooth and continuous at all scales. What if it's not? What if, at extremely small scales we can only probe with the immense energies at CERN space-time, becomes grainy, pixelated, fundamentally discrete? This idea is called quantum gravity, and it's the holy grail of theoretical physics. If space-time has a granular structure at the Planck scale about 10 to the minus 35 meters, then our smooth equations would start breaking down when we look closely enough. Particles would interact with the structure of space-time itself in ways we haven't accounted for. And here's the kicker. If space-time is granular, it might have defects, cracks, flaws in the fabric of reality where the rules change, where constants become variable, where the impossible becomes routine. This isn't wild speculation. Dr. Carlo Rovelli, one of the founders of loop quantum gravity theory, has been saying for years that space-time is probably not continuous. In his view, space and time are emergent properties of something more fundamental, a network of quantum interactions. If he's right, then at high enough energies, we should start seeing effects from this underlying quantum structure. And that's exactly what these CERN anomalies might be showing us. Think of it like a photograph. From a distance, it looks smooth and continuous. But zoom in far enough, and you see individual pixels. Zoom in even further, and you see that each pixel is made of red, green, and blue dots. The smooth image is an illusion created by your brain, stitching together discrete elements. Reality might work the same way. We experience it as smooth because we're not looking closely enough. But CERN is zooming in, and the pixels are starting to show. Now here's what will blow your mind. If space-time is pixelated, then there's a maximum resolution to reality. There's a smallest possible length, a shortest possible time. Below those scales, the concepts of distance and duration stop making sense. And if that's true, then the universe isn't infinite in its divisibility. It's digital at its core. We might be living in a simulation, after all not in the sci-fi sense of being in a computer program run by advanced aliens, but in the more profound sense that reality itself operates on discrete, computational principles. Information might be more fundamental than matter or energy. The universe might be, at its heart, a vast information processing system, and what we call particles and forces are just the observable outputs of that computation. This idea has serious proponents. Dr. Seth Lloyd at MIT has argued that the universe is literally a quantum computer processing information about its own state. Every particle interaction is a calculation. Every moment of time is a clock cycle. A Big Bang was the boot-up sequence, and entropy, the arrow of time, is the accumulation of computational irreversibility. And if the universe is computational, then glitches are possible. Errors can occur. The code can have bugs. The crack that CERN has found might be exactly that. A bug in the cosmic code, a place where the algorithm breaks down and produces results that don't fit the program. Before we go further down this rabbit hole, I need to know you're still with me. If your mind is reeling from these implications, hit that subscribe button, because we're only getting started. We're about to explore what happens when you combine these particle physics anomalies with other strange phenomena that science has been quietly uncomfortable with for decades. And I'm genuinely curious, where are you watching from? And what time is it? Are you in India, watching this at dawn as you prepare for your day? In Brazil, winding down your evening? In the United States, deep in the middle of the night, because you can't stop thinking about these cosmic mysteries? Drop a comment and let me know, because understanding that people all over the planet are grappling with these questions together makes the universe feel a little less lonely and a little more magical. Now, let's connect some dots that most scientists are too cautious to connect in public. The CERN anomalies didn't emerge in isolation. Over the past decade, there have been other experimental results that have made physicists quietly nervous. Results that individually could be dismissed as statistical fluctuations or experimental error, but together paint a disturbing picture of a standard model under siege. In 2021, the Muon G2 experiment at Fermilab found that muons' heavier cousins of electrons behave in ways that deviate from standard model predictions. Muons have a magnetic moment. Think of it as how strongly they respond to magnetic fields. And when measured with incredible precision, this magnetic moment was off by about 0.002%. That's tiny, but in particle physics, that's a massive discrepancy, significant at the 4.2 signal level. Something is influencing muons that we haven't accounted for. Then there's the B meson anomaly. B mesons are particles made of quarks, and when they decay, they should produce electrons and muons at equal rates. That's called lepton universality, a fundamental principle of the Standard Model. But experiments at LHCb at CERN and at Belle 2 in Japan have consistently found that B mesons prefer to decay into electrons rather than muons, violating lepton universality at statistically significant levels. And then there's the proton radius puzzle. When scientists measure the size of a proton using electrons, they get one answer. When they measure it using muons, they get a different answer, about 4% smaller. This shouldn't be possible. A proton is a proton. Its size should be independent of how you measure it. Yet for over a decade, this discrepancy has persisted despite multiple teams trying to resolve it. Do you see the pattern? These aren't random errors scattered across unrelated experiments. There's a thread connecting them. Particles are behaving differently depending on how we interact with them, what we measure them with, and what energies we probe them at. It's as if reality has different rules at different scales, or different rules depending on how you look at it. This sounds suspiciously like quantum mechanics, and that's not a coincidence. Quantum mechanics has always had a measurement problem at its core. The famous observer effect. Particles exist in superpositions of multiple states until you measure them, at which point the wave function collapses into a single state. The act of observation changes reality. We've known this since the 1920s, but we've never been comfortable with it. Dr. John Wheeler, one of the great physicists of the 20th century, proposed something radical in the 1970s, what he called the participatory anthropic principle. The idea is that observers aren't just passive witnesses to the universe, they're active participants in bringing it into existence. Wheeler famously said, "We are participators in bringing into being not only the near and here, but the far away and long go." Consciousness doesn't just observe reality, it actualizes it. This sounds like mysticism, but Wheeler was deadly serious and deeply rigorous. His thought experiments, like the delayed choice experiment, showed that decisions made by observers in the present can apparently influence what happened in the past. Not through time travel, but through the quantum mechanical principle that the past doesn't have a definite state until it's measured. Now combine Wheeler's ideas with what CERN is finding. If observation actualizes reality, and if reality at the fundamental level is showing cracks and inconsistencies, then what does that say about the relationship between consciousness and the physical world? Is it possible that the universe is improvising its own rules as it's being observed? And what we're seeing at CERN is the point where that improvisation is becoming visible. Let me give you an analogy that might help. Think of reality as a video game. When you're playing, the game only renders what's on your screen. The rest of the world isn't computed in full detail. It's approximated, simplified, optimized to save processing power. Only when you turn to look at something does the game render it in full fidelity. The universe might work the same way. Quantum mechanics tells us that particles don't have definite properties until measured. What if that's not a weird quirk of quantum mechanics, but a fundamental optimization principle? Reality only computes the details when someone is looking. The rest of the time, it's running on a low-resolution approximation. And here's where the crack comes in. CERN is looking more closely at reality than anyone ever has before. They're forcing the universe to render details at resolutions it wasn't designed to handle. And just like a video game might start glitching when you clip through walls or push the physics engine too hard, reality is starting to show artifacts, anomalies, cracks in the rendering. Dr. James Gates, a theoretical physicist at Brown University, discovered something fascinating in 2010. While working on supersymmetry, equations a theoretical extension of the Standard Model, he found embedded in the math something utterly unexpected: error-correcting codes. Specifically, codes called double-even self-dual linear block codes, which are the same codes used in telecommunications and web browsers to detect and correct errors in data transmission. Think about what that means. The equations that describe the fundamental forces of nature equations discovered through physics experiments, not invented by computer scientists, contain within them the mathematical structures we use to correct errors in digital information systems. Gates himself said, "This was a real shock." One of the things about this code that is really amazing is that it's error correcting. This is what you do in your browser when you're on the internet. We have to do this, otherwise communication can't happen. We also find the same codes in string theory and supersymmetry. If reality has error-correcting codes built into its mathematical structure, that suggests reality is information-based and errors are possible. The crack at CERN might be the universe's error correction system failing, or it might be us detecting errors that the system hasn't corrected yet. This brings us to an uncomfortable place philosophically. If reality is information-based and potentially glitchy, what does that say about truth? About the reliability of our observations? About the nature of existence itself? For centuries, we've operated under the assumption that there's an objective reality out there that exists independently of observation, and our job as scientists is to discover and describe it as accurately as possible. But quantum mechanics has been whispering for 100 years that this assumption might be wrong. Reality might be fundamentally subjective, not in the sense that you can wish things into existence, but in the deeper sense that the universe doesn't have definite properties until forced to by observation. And now CERN is screaming what quantum mechanics has been whispering. There's something deeply weird about the relationship between observation and reality. And when we push that relationship to its extremes, the neat and tidy laws we've written down start to crumble. What would it mean to live in a universe where the laws of physics are more like habits than rules, where constants aren't constant, but rather statistical trends, where reality is improvised rather than predetermined? It would mean that the future is genuinely open, not just unknown, but undetermined. The universe isn't following a script. It's making it up as it goes along, constrained by certain tendencies and patterns, but not rigidly bound by them. Free will, that controversial concept that neuroscience and determinism have been trying to kill for years, might not just be compatible with physics, but might be a fundamental feature of reality at all scales. It would mean that emergence is more profound than we thought. The way consciousness emerges from neurons, the way life emerges from chemistry, the way complexity emerges from simplicity, these aren't just interesting phenomena. They might be the universe exploring possibility space, actualizing potentials that were previously undefined. And it would mean that we conscious observers, capable of probing reality at unprecedented scales and energies, might be playing a more central role in the story of the universe than we ever imagined. Not because we're special or chosen, but because observation and actuality are entangled at the deepest level. This is heady stuff, and I see some of you skeptics out there thinking, this is getting too philosophical. Show me the math. Show me the mechanisms. Fair enough. Let's get concrete about what exactly is happening at CERN and what the possible explanations are. The Large Hadron Collider has multiple detector systems, each designed to catch different aspects of particle collisions. The two largest are ATLAS and CMS competing detectors designed independently to cross-check each other's results. When both detectors see the same anomaly, that's when you know it's real. In the 2024 data runs, both ATLAS and CMS have been seeing consistent deviations in several channels. The W boson mass anomaly I mentioned, both detectors see it. The B meson decay preference for electrons over muons, both see it. The slight excess of certain events at particular energy levels, both see it. Now, there are conventional explanations being explored. Maybe there's a new particle that couples to both W bosons and B mesons in specific ways. Physicists have proposed various candidates. A Z-prime boson mediating a new force, a leptoquark that transforms between quarks and leptons, a sterile neutrino that doesn't interact through any of the known forces. These are all within the realm of new physics, but still relatively conventional. They extend the standard model rather than breaking it. But here's the problem. Each of these proposed particles would have other effects that we should be able to detect. Z-prime bosons should show up in other decay channels. Leptoquarks should mediate reactions we haven't seen. Sterile neutrinos should have left imprints on the cosmic microwave background. We're looking for these signatures, and so far, they're not there. The anomalies remain isolated, disconnected from the broader tapestry of particle physics. That's what makes Dr. Frank Wilczek's recent comments so intriguing. Wilczek won the Nobel Prize in 2004 for his work on quantum chromodynamics, the theory of the strong force. In a paper published in January 2025, just weeks ago, he proposed something radical. What if these anomalies aren't pointing to new particles at all, but to a variation in the fine structure constant? The fine structure constant, usually denoted by alpha, is one of the most important numbers in physics. It's approximately 1/137th, and it determines the strength of electromagnetic interactions. It's called a constant because, well, it's supposed to be constant everywhere in the universe and throughout all of time. But Wilczek's paper suggests that extremely high energies, the kind achieved at CERN alpha, might not be exactly constant. It might vary by tiny amounts due to quantum corrections from virtual particles popping in and out of existence. If alpha varies, even slightly, it would affect particle decay rates, mass measurements, and interaction cross-sections in exactly the kinds of ways CERN is observing. It wouldn't require new particles. It would just require that one of our supposedly fundamental constants isn't quite as fundamental as we thought. And if one constant can vary, why not others? The speed of light, Planck's constant, the gravitational constant, are any of them truly constant? Or are they all emergent effective values that hold in the low energy regime we normally inhabit but start to shift when we probe the extreme conditions present at the birth of the universe? Dr. João Maguio at Imperial College London has been advocating for a variable speed of light for decades, and he's been largely dismissed by the mainstream. But in light of these CERN anomalies, his ideas are getting a second look. If the speed of light was different in the early universe, it would solve several cosmological puzzles: the horizon problem, the flatness problem, the monopole problem. Problems that inflation theory was invented to solve, but does so in ways that feel contrived to many physicists. A variable speed of light is mathematically consistent with relativity. You just have to reformulate the theory in terms of invariance rather than assuming that C is invariant. And if C can vary, if alpha can vary, if any of these constants can vary, then the crack at CERN isn't just an anomaly to be explained. It's a window into a deeper layer of reality where the rules we've written down are revealed to be approximations, useful but not ultimately true. This is the moment in the video where I need you to pause and really let this sink in. Everything you've been told is solid atoms, forces, the laws of nature might be more like statistical regularities. The universe isn't a machine following fixed laws. It's more like a jazz improvisation, following themes and patterns, but never playing the same way twice. And we're just now getting good enough at listening to hear the variations. If you're feeling like your worldview is cracking right alongside the universe, that's the point. That sense of cognitive dissonance you're feeling, that uncomfortable awareness that something fundamental might be wrong with how you've understood reality. That's what physicists have been feeling for the past year as this data has come in. Welcome to the existential crisis. And smash that subscribe button, because we're about to go even deeper. Let me tell you about something called the vacuum catastrophe, because it's directly relevant to understanding why these CERN anomalies might be symptoms of something much larger and more terrifying. According to quantum field theory, empty space vacuum isn't actually empty. It's seething with quantum fluctuations, virtual particles constantly popping into and out of existence. These fluctuations contribute to the energy density of the vacuum, and when you calculate what that energy density should be using quantum mechanics, you get an answer. Unfortunately, that answer is off by a factor of 10 to the 120. That's not a typo. The theoretical prediction is one followed by 120 zeros times larger than what we observe. This is called the cosmological constant problem, or sometimes the vacuum catastrophe, and it's arguably the biggest failure of theoretical physics. Steven Weinberg, Nobel laureate and one of the architects of the Standard Model, called it a bone in our throat that prevents us from swallowing quantum field theory whole. Why does this matter? Because it suggests that our fundamental theories, quantum mechanics and general relativity, are profoundly incomplete in ways we don't understand. They give spectacularly accurate predictions for certain things, but when you push them to their logical conclusions about the nature of empty space, they fail catastrophically. Now, here's where it connects to CERN. What if the vacuum isn't uniform? What if it has structure, domains, phase transitions like ice forming in water? What if the crack CERN is detecting is a boundary between different vacuum phases, regions of spacetime where the quantum fields settle into different configurations, resulting in different effective values for particle masses and coupling constants? But it would also imply something deeply unsettling. The universe is not homogeneous at the deepest level. There are regions perhaps imperceptibly small in everyday terms, but significant at particle physics scales, where the rules are different. And if vacuum domains exist, if the fundamental fields of nature can settle into different configurations in different places, then the universe is far stranger and more structured than we've imagined. Reality would be more like a patchwork quilt than a uniform fabric. Dr. György Dvali at the University of Munich has been working on related ideas involving what he calls quantum critical points places in spacetime, where quantum effects become magnified and classical notions break down. Near these critical points, Dvali proposes, spacetime itself becomes unstable, fluctuating wildly between different possible configurations. If CERN has created conditions near a quantum critical point, that might explain why they're seeing physics that doesn't match predictions. And here's where it gets really wild. Quantum critical points might not be random features of spacetime. They might be necessary for the universe to compute its own evolution. Think of them as processing nodes in the cosmic computation, places where information converges and reality makes decisions about which of many possible futures to actualize. If that sounds like science fiction, consider this. In 2019, a team of quantum physicists led by Dr. Sabine Hossenfelder published a paper exploring the computational capacity of the universe. They calculated that the observable universe, treating every particle as a quantum bit, could perform about 10 to the 120 operations per second. That's an incomprehensibly large number, but it's finite. The universe has a maximum computational capacity. And if the universe is performing computations, processing information about its own state to determine its evolution, then errors are inevitable. No computational system is perfect. Data corruption happens. Bits flip. And maybe, just maybe, what CERN is detecting is the universe encountering a calculation it can't quite process correctly, a problem that's causing it to return anomalous results. Now, some of you are probably thinking, this is anthropomorphizing the universe. You're treating it like it's a thinking thing, making decisions. And you're right to be skeptical. But let me be precise about what I'm suggesting. I'm not saying the universe is conscious in the way you and I are conscious. I'm saying that the behavior of quantum systems, how they evolve, how they collapse into definite states, how information propagates through them, has mathematical properties that are formally equivalent to computation. The universe doesn't need intention to compute. It computes simply by existing and evolving according to quantum mechanical laws. But here's the kicker. We don't actually know what those quantum mechanical laws are at the deepest level. We have the Schrödinger equation, the path integral formulation, quantum field theory. These are incredibly successful mathematical frameworks. But they're descriptive, not explanatory. They tell us how quantum systems behave, but not why they behave that way. And they certainly don't tell us what wave function collapse actually is, or how observation causes it. The measurement problem in quantum mechanics has been unsolved for 100 years, and it's the elephant in the room in this entire discussion. When a quantum system is in a superposition simultaneously in multiple states, and you measure it, it collapses into one state. But the Schrödinger equation, which governs quantum evolution, is deterministic and reversible. It never produces collapse. Collapse is something extra, something we add to the theory by hand, because that's what we observe experimentally. Various interpretations try to resolve this. The Copenhagen interpretation says, collapse is fundamental, but offers no mechanism. The many worlds interpretation says there's no collapse. The universe splits into branches for each possible outcome. Quantum Bayesianism says collapse is just updating your knowledge, not a physical process. Objective collapse theories propose that gravity or some other mechanism causes spontaneous collapse. None of these interpretations has been definitively proven or falsified. We're stuck in interpretational limbo, with different camps arguing based on philosophical preferences rather than empirical evidence. But what if the CERN anomalies give us a hint about which interpretation is closer to the truth? If reality has cracks, if constants can vary, if the rules are improvised rather than fixed, that sounds most consistent with some form of objective collapse, where quantum systems genuinely transition from indefinite to definite states through a physical process. It suggests that wave function collapse isn't just an artifact of our observation, but is a real event that happens in nature. And when it happens under extreme conditions, like the energies at CERN, it leaves traces we can detect. Dr. Roger Penrose, the Nobel Prize-winning mathematical physicist, has long argued that gravity causes wave function collapse. His theory, called orchestrated objective reduction, proposes that when a quantum system reaches a certain threshold of mass energy, space-time curvature becomes significant enough to force the system to choose one classical state. Consciousness, in Penrose's view, emerges when this quantum collapse happens in the microtubules of neurons. This theory has been controversial, and many physicists dismiss it. But in light of CERN's findings, it's worth revisiting. If space-time curvature can cause collapse, and if CERN is probing regions of space-time with unprecedented energy densities, they might be seeing effects from the boundary between quantum and classical behavior. The crack might literally be the seam where the quantum fabric is forced to collapse into classical reality, and under strain, that seam is showing. What would this mean for consciousness? If observation conscious or otherwise genuinely affects quantum systems, and if those quantum systems are showing anomalies at high energies, then there's a connection between mind and matter that goes deeper than we've acknowledged, not mystical, not unscientific, just a recognition that information, observation, and physical reality are entangled in ways we're only beginning to understand. Let me give you something concrete to hold on to as we navigate these abstract waters. The double-slit experiment is the classic demonstration of quantum weirdness. Fire electrons one at a time at a barrier with two slits. If no one observes which slit each electron goes through, they create an interference pattern on the detector's screen wave-like behavior, suggesting each electron went through both slits simultaneously. But if you observe which slit each electron goes through, the interference pattern disappears particle-like behavior, suggesting each electron went through one slit or the other. This has been done countless times with electrons, photons, even large molecules. The results are always the same. Observation changes the outcome. But here's what's newer. In 2020, researchers at Yale performed a quantum eraser experiment where they showed that erasing information about which path a particle took even after the particle had already been detected could restore the interference pattern. They retroactively changed the past behavior of the particle by changing what information was available in the present. This is Wheeler's delayed choice experiment realized. The present affects the past through quantum correlations. Time, at the quantum level, doesn't work the way we intuitively think it should. Cause and effect get tangled. And if cause and effect can be tangled in controlled lab experiments, what does that say about causation in the larger universe. It says that the block universe view where past, present, and future all exist simultaneously and timelessly might be wrong. It says that the future isn't written. It's being written, moment by moment, through the process of quantum events becoming actualized. And if the universe is writing its own story as it goes, then the anomalies at CERN might be the universe's handwriting becoming visible, showing the corrections and edits being made in real time. Now, you might be wondering, if reality is this fluid, this improvisational, how do we have any stability at all? Why doesn't the universe just dissolve into chaos? And that's an excellent question. The answer is decoherence. Quantum decoherence is the process by which quantum systems become entangled with their environment, causing superpositions to effectively collapse into classical states without any conscious observer needed. It's why you don't see quantum effects in everyday life. Your body is constantly decohering quantum states through its interactions with the environment. Decoherence happens incredibly fast for macroscopic objects, which is why the classical world seems so solid and definite. But decoherence isn't perfect. It's a statistical process, not an absolute barrier. And at the edges, at extreme temperatures, extreme energies, extreme isolation from environment quantum effects can persist at larger scales. Superconductors, superfluids, Bose-Einstein, condensates, these are macroscopic quantum systems where decoherence is suppressed and quantum weirdness becomes visible to the naked eye. CERN is creating conditions at the other extreme, not cold and isolated, but incredibly hot and energetic, recreating the conditions of the early universe. And in those conditions, maybe decoherence works differently. Maybe the boundary between quantum and classical is less clear. Maybe that's where the cracks appear, at the places where reality is still deciding which rules to follow. I want you to sit with that idea for a moment. Reality is deciding, not in a conscious, intentional way, but in the sense that quantum systems evolve according to probabilities. And when those probabilities collapse into actualities, there's a moment of decision. The universe is constantly branching, constantly choosing, constantly actualizing one possibility out of many. And we are part of that process. Every observation you make, every thought you think, every interaction you have with the physical world, you're collapsing wave functions, forcing quantum systems to pick definite states. You're not passive. You're participatory. Before we move into how this affects your daily life and your understanding of existence, I want to make sure you're locked in for the rest of this journey. Hit that like button if this is expanding your mind, and subscribe so you don't miss the next deep dive into reality's mysteries. And seriously, tell me in the comments, where in the world are you and what time is it? Are you in Australia, greeting the morning sun with these cosmic revelations? In Europe, contemplating existence over lunch? In the Americas, letting these ideas echo through your evening? The fact that humans across the entire planet can simultaneously contemplate the fundamental nature of reality is itself a kind of quantum entanglement of consciousness, and I find that beautiful. Now, let's bring this home. Let's talk about what the crack in reality means for you, personally, in your day-to-day life. You might be thinking, okay, particles are behaving weirdly at CERN. Constants might not be constant. Reality might be quantum foam improvising its way through existence. But I still have to pay my bills, eat dinner, and deal with traffic. How does any of this matter to me? Fair question. And the answer is, it matters because how you understand the nature of reality fundamentally shapes how you experience being alive. For the past few centuries, the dominant scientific worldview has been mechanistic materialism. The universe is a deterministic machine. Consciousness is an illusion produced by brain chemistry. Free will is an illusion. Meaning is something we project onto an indifferent cosmos. If that's your worldview, then life becomes a game of optimizing your neurochemistry and accepting your lack of control over anything fundamental. But what if the crack at CERN is showing us that this worldview is wrong? Not slightly wrong, fundamentally, deeply wrong. What if the universe isn't a deterministic machine, but an improvisational creative process? What if consciousness isn't an illusion, but a fundamental feature of reality that participates in actualizing the physical world? What if free will isn't an illusion, but a reflection of the genuine openness of the future at the quantum level? These aren't just abstract philosophical questions. They change everything about how you approach your life. If the future is genuinely open, not just unknown but undetermined, then your choices actually matter in a deep ontological sense. You're not just rearranging the furniture in a predetermined room. You're helping to write the story of the universe. Every decision you make collapses infinite possibilities into a single actuality, and that actuality becomes part of the historical record of what really happened. If consciousness participates in actualizing reality, then the quality of your attention matters. Mindfulness isn't just a psychological trick to reduce stress. It's a way of engaging with the quantum process of reality formation more deliberately. When you're present, when you're aware, when you're observing carefully, you're not just passively receiving information. You're actively participating in the collapse of quantum potentials into definite states. Does this mean you can manifest a Ferrari just by thinking about it? No, don't be ridiculous. The universe has structure, patterns, regularities that emerge from trillions upon trillions of quantum events. Your individual observations are droplets in an ocean, but droplets still affect the ocean. The pattern of waves is shaped by every constituent drop, even if no single drop can claim credit for a tsunami. What you can do is recognize that your subjective experience, your consciousness, your observations, your choices are woven into the fabric of reality, rather than being separate from it. You are not a ghost in a machine. You are a pattern in the quantum field, an eddy in the flow of information through spacetime. And that pattern you has causal efficacy. You matter. Let me give you a concrete example of how this changes things. Think about a difficult decision you have to make. Maybe it's about a relationship, a career move, a creative project. In the mechanistic worldview, there's a correct answer determined by the initial conditions and the laws of nature, even if you don't know what it is. Your job is to calculate the optimal choice and execute it. But in the quantum worldview, there is no predetermined correct answer. There are multiple possible futures, each with different probability amplitudes, and your choice, the act of deciding and committing, collapses those possibilities into one actual future. You're not discovering the right path. You're creating it through the act of choosing. This is simultaneously more terrifying and more liberating than the mechanistic view. More terrifying because there's no cosmic safety net, no guarantee that you'll make the right choice, because there is no right choice until you make it. More liberating because it means you have genuine creative power. The universe hasn't already decided what happens next. You get to participate in that decision. And when you mess up, and you will, because everyone does, it's not because you failed to discover the predetermined path. It's because you actualized a possibility that didn't work out as well as you'd hoped. But that failed path is now part of reality, part of the learning process, and it opens up new possibilities that didn't exist before. Failure isn't a deviation from the script. It's part of the improvisation. Dr. Stuart Kauffman, a theoretical biologist and complex systems researcher, has been developing these ideas in a rigorous scientific framework. His concept of the adjacent possible describes how complex systems like life, consciousness, and economies don't just explore a pre-existing possibility space. They expand that space through their own activity. Each actualized possibility creates new possibilities that didn't exist before. In Kauffman's view, the universe is radically creative. It's not just rearranging atoms according to fixed laws. It's genuinely inventing new forms, new patterns, new organizations of matter and energy that couldn't have been predicted from the initial conditions. Life is the universe becoming creative, Consciousness is the universe becoming aware of its own creativity, and human beings are the universe reflecting on its own nature. Now, Kaufman isn't talking specifically about the CERN anomalies. His work predates them. But his framework provides a way to think about what it means if reality is improvisational at the deepest level. It means that emergence is real. Novelty is real. The future contains possibilities that don't exist yet and can't be calculated from present conditions. And you, yes, you watching this video are one of the mechanisms through which the universe explores those possibilities. This has profound implications for meaning and purpose. In the mechanistic worldview, meaning is something you project onto a meaningless universe. It's a useful fiction that helps you cope with existence. But if consciousness participates in actualizing reality, then meaning isn't just projected, it's participatory. Meaning emerges from the interaction between conscious observers and the quantum field of possibilities. It's co-created by you and the universe together. Your life isn't meaningful because of some cosmic plan or divine purpose. It's meaningful because you're an active participant in the ongoing process of reality creation. Every moment you're alive, you're collapsing wave functions, forcing quantum systems to commit to definite states, adding your contribution to the historical record of what actually happened in this universe. That's not a small thing. That's cosmically significant. You matter not because some external authority has declared you matter, but because mattering is what existence is. To exist is to participate in the actualization of possibility into actuality. And conscious existence awareness of this process is the universe becoming self-aware. Let me connect this to the crack at CERN one more time, because it's important. If reality is showing cracks under extreme conditions, that tells us reality is fragile. Not in the sense that it's about to shatter, but in the sense that it's actively maintained. The regularities we call laws of nature aren't ironclad rules enforced by some cosmic police force. They're emergent patterns that hold as long as the conditions support them. And we conscious observers with increasingly powerful technology are pushing those conditions into regimes they've never experienced before. We're not just discovering pre-existing truths about the universe. We're exploring the edges of what the universe can be, and in doing so, we're participating in determining what it will become. This is both exhilarating and sobering. Exhilarating because it means the adventure is real. We don't know what we're going to find because it hasn't been decided yet. Sobering because it means responsibility is real. Our choices have consequences that ripple through the quantum field and shape the future of reality itself. Some physicists find this interpretation uncomfortable. They prefer the view that there's an objective reality out there that we're slowly discovering, and our role is to be faithful recorders of what already exists. But quantum mechanics has been telling us for 100 years that this view doesn't work. And now CERN is providing evidence that when you push reality hard enough, the neat and tidy picture falls apart. Dr. Christopher Fuchs, a quantum information theorist, has developed an interpretation of quantum mechanics called QBI-SEM, quantum Bayesianism, that takes these ideas seriously. In cubism, quantum states don't represent objective properties of systems, but rather represent an observer's degree of belief about what they'll experience when they interact with the system. Measurement isn't discovering pre-existing facts. It's creating experiences through interaction. This sounds solipsistic, like reality is just in your head. But Fuchs is careful to distinguish between QBI-SEM and solipsism. In cubism, other observers are real, and their experiences are just as valid as yours. But there's no God's eye view, no perspective from nowhere that sees reality as it really is, independent of any observer. Reality is inherently perspectival, and the different perspectives are woven together through quantum correlations that maintain consistency without requiring an underlying objective state. If QBI-SEM is right and the CERN anomalies are consistent with it, then science isn't about discovering the one true description of reality. It's about building models that successfully predict our experiences and coordinate our interactions with each other and the world. And when those models start failing, when anomalies appear that don't fit, it's not a crisis. It's an opportunity to build richer, more nuanced models that capture more of the subtle texture of existence. Now, I'm not saying QBISM is definitively correct. No interpretation of quantum mechanics has been proven definitively correct. But I am saying that the crack at CERN is forcing us to take seriously the possibility that reality is weirder, more participatory, and more alive than the dead, mechanistic universe we've been taught to believe in. And that changes everything about what it means to be human. If you're a pattern in a living, creative, improvisational cosmos rather than a machine in a dead, deterministic one, then everything you do, every kindness, every cruelty, every moment of beauty or banality, contributes to the universe's ongoing exploration of what's possible. You are not insignificant. You are not meaningless. You are not just a collection of atoms following predetermined paths. You are a node in the network of reality creation, and what you do ripples outward in ways you can't fully predict or control, but that matter nonetheless. Before we dive into the final sections where we'll talk about implications for future technology and the long-term fate of the universe, I want to check in one more time. If you're still with me, if your mind is expanding to accommodate these ideas, if you're feeling that electric thrill of understanding something profound about existence, do me a favor, like this video, subscribe to the channel, and drop a comment about where you're watching from and what time it is. Are you in Japan, watching this as dawn breaks over Tokyo? In South Africa, contemplating the cosmos as the sun sets over Cape Town? In Canada, letting these ideas swirl through your mind during a winter evening? Tell me, because knowing that people all over the world are engaging with these questions makes the universe feel less lonely and more like the collaborative exploration it truly is. Now, let's talk about what comes next. If the crack is real, if reality is improvisational, if constants aren't constant, what does that mean for the future of science and technology? First, it means we need new physics. The Standard Model has been the reigning champion for 50 years, explaining everything we've seen with incredible precision. But if CERN is finding cracks in it, then we need a new framework that can explain both the successes of the Standard Model and the anomalies that are appearing. Several candidates are waiting in the wings. String theory proposes that fundamental particles aren't point-like objects, but tiny vibrating strings, and the different vibration patterns correspond to different particles. It naturally includes gravity, which the Standard Model doesn't, and it predicts extra dimensions of space beyond the three we experience. But string theory has been criticized for being too flexible. It can accommodate almost any set of observations, which makes it hard to falsify. It predicts a vast landscape of possible universes, perhaps 10 to the 500 of them, with different physical constants in each one. We just happen to live in one of the rare universes where the constants allow for life. Loop quantum gravity takes a different approach, focusing on quantizing spacetime itself rather than treating it as a smooth background. It predicts that space is granular at the Planck scale, made of discrete units called spin networks. This could explain the CERN anomalies if we're starting to probe energies where the granular structure of spacetime becomes relevant. But loop quantum gravity struggles to incorporate the Standard Model particles and forces in a natural way. Then there's emergence theory, championed by physicists like Sean Carroll. The idea is that spacetime and quantum fields aren't fundamental, but emerge from something more basic, perhaps information, perhaps quantum entanglement, perhaps something we haven't even thought of yet. In this view, the laws of physics aren't discovered. They're derived from deeper principles about how information organizes itself. The CERN anomalies might be showing us the edge of the emergent regime, where the underlying substrate starts peeking through. Each of these frameworks has strengths and weaknesses, and none of them has been confirmed experimentally until now, potentially. If the CERN anomalies persist, and if we can determine which theoretical framework best explains them, we'll have the first real experimental evidence pointing us toward the correct theory of quantum gravity. That would be Nobel Prize material several times over, and would fundamentally reshape our understanding of reality. But beyond the academic excitement, there are practical implications. Understanding how spacetime can have cracks, domains, or variations in its fundamental properties opens up possibilities that sound like science fiction, but might be science fact. Consider wormholes. General relativity allows for solutions where spacetime connects distant regions through shortcuts Einstein-Rosen bridges. But the math shows that such structures require exotic matter with negative energy density to hold them open. We've never found such matter, so wormholes remain theoretical curiosities. However, if vacuum domains exist, if the quantum fields can have different configurations in different regions, then the boundaries between those domains might naturally have the exotic properties needed to stabilize wormhole throats. The crack that CERN found might be the first evidence of vacuum domain boundaries, which could mean that shortcuts through spacetime aren't just mathematically possible, but might be physically realizable. I'm not saying we'll be building warp drives next year. The energy scales required would be astronomical, and even if it's possible in principle, engineering it in practice is a whole different challenge. But it shifts wormholes from absolutely impossible to maybe possible if we're very clever, which is a significant upgrade. Similarly, consider time travel. The laws of physics, specifically general relativity, don't prohibit time travel. There are solutions called closed time-like curves where you can travel into your own past. But these solutions require exotic matter or require the universe to have properties we haven't observed. If spacetime is more malleable than we thought, if the constants of nature can vary, if reality is improvisational at the edges, then maybe time travel isn't as impossible as we've assumed. Again, I'm not saying it's easy or even likely, but the crack at CERN is showing us that reality is weirder than we thought. And historically, whenever we've discovered reality is weirder than we thought, that weirdness eventually becomes the foundation for new technologies. Quantum mechanics seemed like abstract weirdness a century ago. Now it's the basis for transistors, lasers, MRI machines, and quantum computers. Who knows what technologies might emerge from understanding how spacetime can crack and vary? Speaking of quantum computers, let's talk about them, because they're directly relevant to this discussion. Quantum computers exploit quantum superposition and entanglement to perform certain calculations exponentially, faster than classical computers. They work by putting quantum qubits into superpositions of 0 and 1 simultaneously, then letting those superpositions interfere with each other to explore multiple computational paths at once. But quantum computers face a serious challenge: decoherence. The qubits need to maintain their superposition for long enough to complete the calculation, but any interaction with the environment causes decoherence, collapsing the superposition and ruining the computation. Current quantum computers require extreme cold and isolation to minimize decoherence, and even then, they can only maintain coherence for microseconds. What if understanding the crack at CERN, understanding how quantum and classical regimes interact, how observation causes collapse, how spacetime itself might have granular structure, leads to better methods for controlling decoherence? What if we can engineer quantum systems that maintain coherence longer by exploiting the physics of vacuum domains or quantum critical points? We're talking about quantum computers that can factor large numbers, breaking current encryption schemes. Quantum simulations that can model molecular behavior atom by atom, revolutionizing drug design. Quantum sensors that can detect gravitational waves, dark matter, or even variations in the fine structure constant. The practical applications would be transformative. But there's a darker side to these possibilities. If reality is improvisational and consciousness participates in actualizing it, then technologies that manipulate quantum states at scale could have unpredictable effects. We're not just rearranging furniture anymore. We're potentially influencing the process by which reality decides what's actual. Dr. Nick Bostrom at Oxford has written about existential risks from advanced technology, ways that human innovation could accidentally destroy us or transform us beyond recognition. He talks about risks from artificial intelligence, nanotechnology, biotechnology. But he hasn't really addressed quantum risks, the possibility that probing or manipulating quantum systems at large scales could trigger phase transitions in vacuum domains, or nudge the Higgs field closer to instability, or open up regions of spacetime where the laws of physics are different. The crack at CERN might be a warning. Be careful how hard you push reality. It's more fragile than you think. Not in the sense that it's about to shatter, but in the sense that it can be permanently altered in ways we can't undo. This isn't an argument against continuing research at CERN or building more powerful particle accelerators. Scientific curiosity is one of humanity's greatest virtues, and understanding the universe is worth some risk. But it is an argument for proceeding thoughtfully, with awareness that we're not just passive observers anymore. We're active participants, and our observations and interventions have consequences. Let's zoom out even further and think about the long-term fate of the universe in light of these discoveries. Cosmology tells us that the universe is expanding, and that expansion is accelerating due to dark energy. In the standard model of cosmology, if this continues, we're headed for a big freeze, a future where galaxies drift apart, stars burn out, black holes evaporate, and eventually all structure dissolves into a cold, dark, empty void. Heat death, entropy maximized. Nothing left but quantum fluctuations in an endless expanse of near-perfect vacuum. Cheerful, right? But this prediction is based on the assumption that dark energy is constant and that the laws of physics don't change. If CERN is showing us that constants can vary, then all bets are off. The fate of the universe is suddenly much less certain. If the vacuum is metastable balanced, like a pencil on its tip, it could collapse into a lower energy state at any time, triggered by quantum fluctuations or by high-energy particle collisions. That collapse would expand at the speed of light, and everything in its path would be annihilated as the fundamental constants shift to new values. This is called vacuum decay, and it's a possible way the universe could end much sooner than heat death would suggest. On the other hand, if vacuum domains exist, the universe might be much more resilient than we think. Different regions might have different physical constants, and life and structure might be possible in domains other than our own. The universe might not end so much as transform, passing through phase transitions into configurations we can't currently imagine. Dr. Freeman Dyson, the legendary physicist, spent the latter part of his career thinking about the far future. He imagined ways that intelligent life might survive indefinitely, even in an expanding, cooling universe exploiting energy gradients, transitioning to slower and slower timescales, persisting as information patterns rather than biological organisms. Dyson's scenarios assumed fixed laws of physics. But if those laws can vary, if reality is improvisational, then the possibilities expand dramatically. Maybe consciousness can survive not just by adapting to the dying universe, but by participating in its transformation, helping to actualize configurations of spacetime that support continued complexity. This might sound fantastical, but remember, consciousness already participates in collapsing quantum states. If the universe is quantum mechanical all the way up, and the evidence increasingly suggests it is, then conscious observation isn't a peripheral phenomenon. It's central to how reality operates. And if humanity or its descendants survive long enough to become cosmically influential, we might play a role in shaping the far future of the universe itself. Dr. John Barrow explored what he called the anthropic cosmological principle, the idea that the universe must have properties compatible with conscious observers, because otherwise we wouldn't be here to observe it. But he took it a step further. Maybe the existence of observers isn't just a selection effect. Maybe observers are necessary for the universe to fully exist. Maybe the quantum universe requires observation to collapse its wave function, and conscious life is the mechanism through which the universe actualizes itself. In this view, the appearance of life and consciousness isn't a cosmic accident. It's an inevitable consequence of quantum mechanics operating at cosmic scales. The universe needs observers to exist in definite states rather than superpositions of possibilities. And if that's true, then the emergence of intelligent life is written into the fabric of reality at the deepest level. Not because of divine plan or cosmic purpose, but because of the quantum mechanical relationship between observation and actuality. The crack at CERN hints at this. If reality is showing stress fractures when we probe it without sufficient observation, or when we create conditions that exceed what normal matter and energy can handle, maybe we're seeing the limits of what an unobserved universe can sustain. Maybe reality needs consciousness to stabilize it, and the anomalies are appearing in regimes where that stabilization breaks down. This is speculative, obviously, but it's speculative in a scientifically interesting way. It makes predictions that could potentially be tested. If observation stabilizes quantum systems, then we should see different results in particle collisions depending on how closely we're monitoring them. If vacuum domains are real, we should be able to map them and predict where anomalies will appear. If spacetime is granular, we should eventually be able to measure that granularity directly. These are experiments for the next generation of particle accelerators and space-based observatories. CERN is planning upgrades that will increase collision energies and data collection rates. The James Webb Space Telescope and its successors will probe the early universe with unprecedented precision. Gravitational wave detectors like LIGO will map the curvature of spacetime. Over the next few decades, we'll gather data that could confirm or refute these ideas. And if they're confirmed, if we definitively show that reality is improvisational, that consciousness participates in actualization, that the universe is more alive than dead, then we'll face a philosophical revolution as profound as any in history. Copernicus dethroned Earth from the center of the universe. Darwin showed that humans are part of the natural world, not separate from it. Quantum mechanics suggested that observation affects reality. And now we might be on the verge of understanding that the observer and the observed are woven together so intimately that they can't be separated. Not just epistemologically, but ontologically. You are not in the universe. You are part of the universe, and the universe is not separate from you. It's actualizing itself through your observations, your choices, your conscious engagement with existence. Before we wrap up, I want to make sure you understand how radical this shift in perspective truly is, because I don't think most people appreciate the magnitude of what's being suggested here. So let me make it as concrete as possible. Think about a moment in your past that you remember vividly. Maybe it's a childhood experience, a meaningful conversation, a turning point in your life. You remember it as something that definitely happened, right? It's part of your history, fixed and unchangeable. But according to quantum mechanics and the delayed choice experiments I mentioned earlier, the past doesn't have a definite state until it's observed. Your memory of that event is an observation that collapses the quantum superposition of possible pasts into one actual past. Before you remembered it, the event existed in a kind of quantum limbo, neither definitely one way nor another. This sounds crazy, but it's what the math of quantum mechanics suggests, and experiments support it. The past is actualized by observation in the present just as much as the future is. Time isn't the rigid, linear, one-way street we intuitively experience. It's a much more fluid and interconnected structure where past, present, and future are all involved in a dance of mutual determination. If that's true, if your memories are literally helping to determine what actually happened in your past, then you have more creative power than you've ever imagined. Not the power to change events, but the power to determine which version of ambiguous events becomes real through the act of remembering and interpreting them. Did that person mean to hurt you? Or were they just thoughtless? A quantum multiverse contains both possibilities and superposition until you collapse that superposition through the act of deciding which interpretation to adopt. And once you've collapsed it, that interpretation becomes part of your actual past, shaping your identity and your future choices. This isn't just pop psychology dressed up in quantum language. This is taking seriously what quantum mechanics tells us about the relationship between observation and actuality, and applying it to the human experience of time and memory. And here's where it connects back to CERN. If consciousness can actualize the past through memory, and if CERN is finding cracks where the rules of actualization are breaking down or becoming visible, then we're glimpsing the mechanism behind a process we've been unconsciously participating in our entire lives. Reality creation isn't just something that happens in particle accelerators. It's something that happens in your mind every moment you're conscious. The crack at CERN is showing us the seams in the fabric of reality. And once you see the seams, you can never unsee them. You can never go back to the naive view that the world is just out there, solid and definite and independent of you. You're implicated. You're involved. You matter. And that's ultimately why this discovery is so significant. Not just because it challenges the standard model or opens up possibilities for new physics, but because it transforms how we understand ourselves. We're not passengers on a predetermined journey through a mechanical universe. We're co-creators of reality itself, participating in an improvisational exploration of what's possible. Every choice you make matters. Every observation you make matters. Every moment of consciousness matters. Because they're all contributing to the grand project of actualizing reality from the quantum foam of possibility. You are not insignificant. You are not meaningless. You are not just a machine executing a program. You are a pattern in the universe that is aware of itself, capable of reflecting on its own nature, capable of participating consciously in the process of reality creation. The crack at CERN is a crack in the illusion of separation. It's showing us that the observer and the observed are entangled, that consciousness and matter are woven from the same quantum fabric, that existence is an ongoing creative process in which we are all participants. As we come to the end of this journey together, I want to leave you with a sense of wonder and possibility rather than existential dread. Yes, reality might be more fragile than we thought. Yes, we might be living in a universe that's improvising its own rules. Yes, the constants of nature might not be constant, and the laws of physics might be more like habits than commandments. But that doesn't make existence any less real or meaningful. If anything, it makes it more so. Because it means the universe is alive in a way we've barely begun to appreciate. Not alive like a biological organism, but alive in the sense of being creative, exploratory, generative. The universe is doing something. It's becoming. And we're part of that becoming. The crack at CERN is a gift. It's reality showing us its inner workings, inviting us to understand ourselves and the cosmos more deeply. Yes, there are risks. Yes, there are unknowns. But there are also possibilities we can't yet imagine. Technologies we haven't invented. Understandings we haven't achieved. Futures we haven't actualized. And you, yes, you get to be part of discovering and creating those futures. Not because you're special or chosen, but because being alive and conscious automatically makes you a participant in the grand adventure of existence. So what should you do with this knowledge? How should you live differently knowing that reality is improvisation rather than mechanism? First, take your choices seriously. They matter in a deep ontological sense. You're not just rearranging pre-existing elements. You're helping to determine which elements become actual. Second, cultivate awareness. Mindfulness practices, meditation, contemplative prayer, or simply paying closer attention to your moment-to-moment experience. These aren't just psychological techniques. They're ways of engaging more consciously with the quantum process of reality formation. Third, embrace uncertainty. If the future is genuinely open, then not knowing what happens next isn't a problem to be solved. It's the nature of existence. Learn to be comfortable with improvisation, with making it up as you go along, because that's what the universe itself is doing. Fourth, connect with others. If we're all nodes in the network of reality creation, then our interactions matter. Every conversation, every relationship, every moment of genuine connection is part of how the universe explores what's possible in the realm of intersubjectivity. And fifth, stay curious. The universe is weirder than we think, and it's probably weirder than we can think. There are mysteries within mysteries, depths beneath depths. The crack at CERN is just the beginning. Who knows what we'll discover next? The Large Hadron Collider will continue running experiments. Physicists will continue analyzing data. Theorists will continue proposing new frameworks. And gradually, piece by piece, we'll understand more about the crack and what it means. Maybe it will lead to new physics that unifies quantum mechanics and gravity. Maybe it will lead to technologies we can barely imagine. Maybe it will lead to a fundamental rethinking of what existence is and what it means to be conscious. Whatever happens, we're living through a pivotal moment in human history. A moment when our understanding of reality is shifting at its foundations. And you got to be here for it. You got to contemplate these mysteries, to let your mind expand to encompass the vastness and weirdness of existence, to feel that vertiginous thrill of glimpsing the infinite. That's a privilege. That's a gift. That's what it means to be alive at this particular point in the universe's evolution. So thank you for joining me on this journey through the crack in reality. Thank you for staying curious, staying engaged, staying open to the possibility that everything you thought you knew might be wrong in the most beautiful and profound ways. If this video expanded your mind, if it changed how you see yourself in the universe, do me a favor. Like it, share it, subscribe to the channel. Leave a comment telling me where you are in the world and what time you're watching this. Tell me how these ideas land for you. Tell me what questions they raise. Tell me what you're going to do differently now that you know reality is improvisation. Because we're all in this together, all of us conscious nodes in the network of reality creation, all of us participating in the grand adventure of existence, all of us co-creating the future moment by moment. The crack at CERN unravels everything we thought we knew. But in that unraveling, there's an opportunity to weave something new, something richer, something more true to the actual nature of existence. The universe is stranger than we imagined, more alive, more creative, more participatory. And you, yes, you are an essential part of that strangeness, that aliveness, that creativity, that participation. Never forget that. Never doubt that. You matter. Your choices matter. Your consciousness matters. You're not separate from reality. You're one of the ways reality knows itself. And that, ultimately, is what the crack at CERN has revealed. Not that reality is breaking, but that it was never as solid and separate and mechanical as we thought. It's fluid. It's alive. It's us. Welcome to the adventure. It's just beginning.